tell you a survey of some results here. And finally, I'll tell you about some exciting new work that makes progress on the parallel repetition question. This is based on a joint work with Justin, Kunal, Raz and Wei. So most of this talk, I'm just going to be telling you a lot of results and what's happening in this field. And in the last 10-15 minutes or so, depending on time, I'll tell you a little bit about the connections of this problem to other areas and a little bit about our proof strategy. So let's start with what is multiplayer parallel repetition. What is a multiplayer game? Let me mute my computer so I don't hear myself twice. Okay. So what is a multiplayer game? You have a verifier and you have k players. These k players do not communicate with each other. When k is 2, we call it a two-player game. When k is at least 3, we call it a multiplayer game. Each player receives some input from some finite set. The inputs for the different players are sampled from some joint distribution, and each player has to produce an answer. The goal of the players is to satisfy some predicate V that depends on the questions and the answers to all the players. More formally, you have a distribution mu. The verifier samples an input x1 up till xk from mu and sends xi to player I. Player I looks at xi and produces an answer ai. So ai is purely a function of xi, and their goal is to satisfy this predicate v of x comma a. We say that the players win on input x if the predicate evaluates to 1, and we say they lose on input x if this predicate evaluates to 0. We define the value of the game to be the maximum probability of winning. In most of the games we study, it's not going to be possible for the players to win on all the inputs, so they're going to try to maximize the probability of winning, where this probability is with respect to this distribution mu on the inputs. The maximum here is over all possible player strategies. Let me tell you a little more about the strategies. So by a strategy, we mean a function that tells the player what to output on any input. It's a function that maps xi to ai. We could consider games where we have randomized strategies. That is, the players are allowed to sample a public random string, and based on that random string, they're allowed to come up with answers. But you can show by linearity of expectation that by fixing the randomness, you can produce deterministic strategies that do at least as good. So we can assume for the rest of the talk, without loss of generality, that the strategies are deterministic. We can also assume that everybody knows the strategy. This is because the players are trying to win the game. They can agree on the best strategy beforehand and play according to that strategy. So this is the definition of a multiplayer game. Just to emphasize here what is known and what is unknown. This distribution mu is known to everyone. The predicate V is also known to everyone. And as I just said, we can assume that the strategies are known to everybody. They agree on a strategy and then play according to that strategy. The only unknowns here are what input the other player receives. So player I is the only one who knows what xi is, and the verifier, of course. So xi and ai are known only to the verifier and player I. So this is the unknown here. So what is the motivation for studying multiplayer games? So these were first introduced in computer science in the context of multi-prover interactive proofs, where you think of the players as the provers and the verifier is just some polynomial time algorithm. These have also been studied in physics in the context of non-local games and Bell inequalities. Given the nature of this workshop, I'm going to tell you a little more about the second motivation. So what do multiplayer games have to do with Bell inequalities? To do this, to explain this, I need to first define what the quantum value of a game is. So what is a quantum game? The setting is very similar to before. The only difference is that Alice and Bob are allowed to share an entangled state. They're allowed to agree on some arbitrary entangled state and then use that state. So what they're going to do is once they receive inputs, they're going to measure the state, measure parts of the state, and then based on the measurement outcome, they're going to produce an answer. So we can define the quantum value of a game to be the maximum probability of winning when the players are allowed to share an entangled state. Here the maximum is over player strategies as well as the entangled state. And the probability is, as before, it's over the inputs drawn from this distribution mu, and also over the measurements that induce probabilistic outcomes. So just to emphasize here, this entangled state is something the players decide beforehand. This is independent of their inputs. They just fix some entangled state, the best possible entangled state. The measurement that Alice and Bob perform is allowed to depend on their inputs. So based on the inputs that they receive, they apply some measurement operator, and based on the outcomes, they can come up with answers. So this is a quantum game. We can view Bell inequalities and Bell's theorem as giving examples of games for which the quantum value is strictly bigger than the classical value. This was not the language in which it was originally studied, but it can be phrased in this language. To give you a little more intuition on why this result is so interesting. So quantum mechanics involves some degree of uncertainty and probability. This was a source of concern for many physicists, including Einstein, who famously said that God does not play dice. So along with Rosen and Podolsky, he came up with this alternate theory called the hidden variable theory. He said that all uncertainty in quantum mechanics actually comes from these hidden physical quantities that we cannot measure, and everything else is a deterministic function of these hidden quantities, loosely speaking. This theory was disproved. The first nail in the coffin for this theory was by Bell. He showed an experiment which cannot be explained by the hidden variable theory, but which can be explained by quantum mechanics. He showed that all hidden variable theories must satisfy something called Bell inequalities, but quantum mechanics allows violations of these Bell inequalities. So there are many such examples now we know that show this separation, and this has been put to test in real life. So this is strong experimental evidence that the uncertainty in quantum mechanics doesn't come from some hidden physical quantities that we cannot measure, but rather this uncertainty is inherent to this model. This was an important discovery in quantum mechanics that shed light on the nature of quantum. And it turns out that these discoveries can be phrased in the language of non-local games. These discoveries can be viewed as giving examples of games whose quantum value is strictly larger than the classical value. Let's see an example of such a game. This game will also be interesting to us from the perspective of parallel repetition. So the game we're interested in is the GHZ game. Here, a verifier samples an input x, y, z uniformly at random from these 4 points, 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. So the question to each of the player is either 0 or 1, and the questions are correlated in this fashion. The players need to come up with bits A, B, and C such that this predicate is satisfied. The XOR of A, B, and C equals the OR of X, Y, and Z. This is the GHZ game. You can show that the classical value of this game is 3/4. Consider a strategy where all the players always answer 1. This strategy wins on all points except 0, 0, 0. So here is a strategy that wins with probability 3/4. You can show that there is no strategy that wins on all 4 points. So the value of this game is exactly 3/4. Interestingly, the quantum value of this game is 1. If Alice, Bob, and Charlie are allowed to share an entangled state known as the GHZ state, they can actually win this game with probability 1. This is an example of a game that shows a Bell inequality violation. Now that I've defined multiplayer games, let me move on to parallel repetition. So any questions about the definition of a multiplayer game? So what is parallel repetition? So in parallel repetition, there are still k players and one verifier, and now they're playing n independent and parallel instances of the game, and their goal is to win all the instances simultaneously. More precisely, the verifier samples n independent inputs from this distribution mu and sends the ith part of all the instances to the ith player. The ith player comes up with answers for all the n instances, and the goal of the players is to win all the games simultaneously. That is, the predicate for the bigger game is the AND of the predicate for the individual games. As before, we can define value of g to the n as the maximum probability of winning all the instances simultaneously. Here, the probability is over mu to the n, and the maximum is over strategies for the n-fold game. One thing to note here is that the answers that the players give on the first instance can depend on the questions they receive to the other instances. So, for example, A11 can depend on all of x11 up till x1n. The parallel repetition question is this: what is the asymptotic behavior of value of g to the n as n goes to infinity? This is a very natural question to ask. You have a multiplayer game. One thing you could do is to try to repeat it in parallel and hope that the value goes down. The parallel repetition question asks, how fast does the value go down? Does it even go down at all? So this has a lot of applications. One application in the context of a quantum information is the following. You can amplify the gap between quantum and classical value. If you could do parallel repetition, you could take a game that shows a Bell inequality violation. So let's say you have a game whose quantum value is 1 and classical value is less than 1. By repeating it in parallel, using parallel repetition, you can amplify the gap. You can produce a game whose quantum value is 1, but classical value is as small as you want it to be. For two-player games, this question has a lot of applications in computer science. It has applications to PCPs and hardness of approximation. It has applications to geometries of form and on tiling the space. It also has connections to communication complexity and information complexity. For games with 3 or more players, a recent work of Kunal and Ran showed that this problem has application on Turing machine lower bounds. That is, if you can show parallel repetition for a particular multiplayer game, you get a superlinear lower bounds for non-uniform Turing machines. There's also some general intuition in the field that the techniques here might find other applications, possibility to direct some results in number on 4 at communication complexity. So the kind of bottlenecks you encounter while proving parallel repetition are reminiscent of bottlenecks in other hard problems in communication complexity. So there is a hope that you might use techniques here in other areas. So these are reasons to study the parallel repetition question. What do we know about parallel repetition? So one easy thing is that value of g to the n is at least value of g to the power n. If each of the players just play each instance independently, they can do at least as good as value of g to the power n. You might expect that value of g to the n is at most value of g to the power n, but as you can imagine, this is not the case. There are games which you can win the parallel game much better than just running each instance independently. So let's see an example of a game that shows this violation. This example will be good to keep in mind as it shows what are the difficulties in proving parallel repetition. So let's look at this example. So here is a 2-player game. The verifier samples inputs x, y uniformly at random from 1, 2, 1, 2. So each x and y is an element of 1, 2, and x and y are independent. Alice gets x, Bob gets y. Alice and Bob need to answer I, a and j, b such that they both answer the same thing. Furthermore, if I equals 1, then x equals a. If I equals 2, then y equals a. So what this is saying is that Alice and Bob need to agree on a common I, a such that the ith player got a as the input. So this is the game. You can show that the value of this game is exactly half. So imagine that Alice announces 1, x, where x is her input, and Bob outputs 1, a random bit. With probability half, this random bit is going to equal the one that Alice received. So with probability half, this strategy is going to win. You can show that any strategy that does well in this game essentially involves one of the players guessing the other player's input. So the value of the game is at most half. So therefore, this is a game with value half. You can show that repeating this game twice does not decrease the value at all. So here is a strategy that wins the repeated game with probability half. And the strategy is the following. Alice is going to answer 1, x1 for the first game and 2, x1 for the second game, where x1 is her input to the first game. Bob is going to answer 1, y2 for the first game and 2, y2 for the second game, where y2 is his input for the second game. Now, with probability half, x1 is going to equal y2, in which case they win both instances of the game. So here is a game where repeating it twice does not decrease the value at all. What is happening here is that the players' answers for the other games depend on their inputs to other games. So here Alice's answer for the first game, for the second game, depends on her input to the first game. As a result, the players are able to introduce correlation between the different instances of the game. Therefore, the games no longer behave independently. So this is what makes parallel repetition so hard to prove. The players can introduce correlation between the different instances of the game, and it's not clear how to handle this. So any questions about this example? Okay, so what do we know about the parallel repetition question? For two-player games, we know that the value decreases exponentially fast. This was conjectured by Feige and Lovash, and the celebrated parallel repetition result of Raz, later simplified by Holenstein, shows that for any two-player game, if the value is less than 1, then parallel repetition decreases the value exponentially fast. We now know better results in terms of the value of the original game. So we know a better understanding of the connection between C and the value of the original game. So for two-player games, the situation is pretty well understood. For three-player games, it's much less understood. The best result we have that applies to arbitrary three-player games, multiplayer games actually, is the following result. So this is due to Verbitsky. He shows that if you have a multiplayer game with value less than 1, then parallel repetition decreases the value. And how fast is a very slow quantity, slowly growing quantity. It's 1 over the inverse Ackermann function. So this is a very slow rate of decay, but this is the only provable rate of decay that we have. So this is by an application of the density-Hales-Jewett theorem. What about other special classes of multiplayer games for which we have better results? Well, for free games, we have better results. So free games are games where this distribution mu is a product distribution on the player's inputs. So each player's input is independent of the other player's inputs. Then we have good parallel repetition bounds. For a more general class of games known as expanding games, which I will get to soon, we also know an exponential decay. So this result by Dinur, Harsha, Venkat, and Yuan shows that you can lift two-player parallel repetition techniques to expanding games. Let me present the result in the simpler context of connected games. So let's look at connected games. What are these games? Given a game G, you define a graph whose set of vertices is basically this is the set support of mu. So for every input that occurs with non-zero probability in this distribution mu, you put a vertex. You connect two vertices if they differ on the questions to exactly one of the players. You call G a connected game if this graph is connected. So let's look at an example. So here is the GHC game, which we already introduced. The inputs to the GHC game are 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. To get from any one input to the other input, you need to change the questions to at least two players. So this is a highly disconnected game. On the other hand, in the first example, you have a game where the support of the distribution is just, input distribution is just 0, 0, 0, 0, 1, 0, 1, 0, 0, and 0, 0, 1. And you can show that this graph is a connected graph. So this is a connected game. What Dinur, Harsha, Venkat, and Yuan showed is that for all connected games, you can use two-player parallel repetition techniques and show that actually for connected games, parallel repetition decreases the value at least exponentially fast. This was pretty much the state-of-the-art result with regards to multiplayer games prior to our work. So I'm now ready to present our main result. In a series of works, we show that for all three-player games, where the inputs to each player are either 0 or 1, parallel repetition decreases the value at least polynomially fast. So this is our main result. I'll go into a few examples and applications of this, but this is the main takeaway of our works. The way we do this is by trying to understand all possible games on three players with binary inputs, and pretty much for each class of game, we come up with a new proof technique. So any questions about our main result?
There's no size on the return on the answers.
We get a bound that depends on the size of the answers. So, but it works no matter how large so any constant sized alphabet would work.
And this is exactly without correlations. So there is entanglement or non-signaling correlations.
Oh, yeah, we do not know about the quantum value of the game. Yeah. Yeah, for non-signaling, it turns out that you can't always prove parallel repetition. So, yeah.
Do you think this is optimal?
No, one might hope that you can actually prove exponential decay. I think it will be very interesting to come up with examples where exponential decay does not hold, although I don't think that's true. Okay, so let's see a few examples of games for which our result applies. So the first example is what we call player-wise connected games. This is a generalization of connected games. Here is a definition. So given a game, you define a graph for each player where the ith graph consists of inputs to the ith player. You connect two inputs xi and x prime I if there is an input x minus I to the other players, such that both xi x minus I and x prime I x minus I are in the support of mu. You call a game player-wise connected if all of these graphs are connected. So you can show that all connected games are player-wise connected games, but player-wise connected games need not be connected. And this is the example. So this definition might seem a little vague. So let's see an example of this definition in action. So let's show that this game is actually player-wise connected. So what does it mean for a game to be player-wise connected? Let's first look at Alice's possible inputs. These are 0 and 1. We ask if there is a setting of the other inputs that connects 0 and 1 for Alice, and indeed there is. If you look at the input 0, 0, 0 and 1, 0, 0, this just flips Alice's coordinate from 0 to 1, and all the others are the same. So this shows that Alice's possible inputs are connected. Similarly, you can show that Bob's possible inputs are connected, and Charlie's possible inputs are connected. So this is a player-wise connected game, and our result implies that parallel repetition decreases the value at least polynomially fast. Some remarks about this result. Our result actually applies for any number of players, and the inputs can be arbitrary. Any finite alphabet works. So this is what we have for player-wise connected games. Our second application is for the GHZ game. So I already defined what the GHZ game is and showed you some motivations for studying this game in quantum information. This question is also interesting in the parallel repetition literature. So this previous work of Vinur, Harsha, Venkat, and Yuan highlighted the GHZ game and said that if you want to make progress on the general parallel repetition question, we first need to start with the GHZ game, because this is very far from connected games. This is very far from the problems for which we can apply two-player parallel repetition techniques. So this result was first proved by Justin and Ran. In a later work, we simplified the proof of this and showed that parallel repetition decreases the value at least polynomially fast. And our result applies for any game on the GHZ distribution, not just the GHZ game, but any game with value less than 1. So if we have time, I'll tell you a little bit more about our proof technique and how this problem connects to other combinatorial problems. Let me mention two other results for which we have applications. A third application is to this distribution. So if you take these 4 points, we show a parallel repetition theorem for games on these 4 points. This is just one of the distributions that came out when we were trying to understand what all possible hard distributions are there on 3-player games, binary inputs. Another interesting game that came about is the anticorrelation game. So here the inputs are 0, 0, 1, 0, 1, 0, and 1, 0, 0. And the game is the following. Each player has to output a bit such that the two players who got 0 must output different bits. This is called the anticorrelation game. It's not too hard to show that the value of this game is 2/3. So for example, if Alice and Bob always agree to output 0 and 1 respectively, then you can argue that this wins with probability 2/3. And no matter how the players play, they cannot win with probability more than 2/3. Interestingly, Fourier showed that if you repeat this game 3 times, the value does not go down. So this is the anticorrelation game. So Justin and Lisa studied the so-called non-signaling value of this game. I'm not going to define what that is, but it is something that is motivated by the definition of quantum value of a game. It satisfies this inequality that it is at least the quantum value of the game. And Lisa and Justin showed that this value does not decrease at all under parallel repetition. What we show is that the classical value actually decreases exponentially fast. We also show that this is in some sense the hardest game when the players need to output bits. And we show that parallel repetition holds for this game. We also study games on the same distribution with longer outputs. It turns out that there is a game called the k-bit anticorrelation game. The definition is not important, but this is the hardest game, so to speak, on 3-player 3-point distribution where the outputs are k-bits long. And we show that parallel repetition for this game decreases the value at least polynomially fast. Just to pictorially depict our results. So earlier we had the class of 2-player games for which we knew parallel repetition. the techniques for two-player parallel repetition can be lifted to work for connected games. What we show is those techniques can be lifted with additional ideas for player-wise connected games. We also come up with a new proof for the parallel repetition for the GHC distribution and the 4-point distribution. For these three distributions. So any questions about our results?
Did you say what free games are?
Yes, so free games are games where the players' inputs are independent of each other. Okay. So in the rest of this talk, I'm just going to focus on the GHC distribution and tell you about some of the ideas behind the proof of this. Yeah, so some of these comments have already been covered, which is, okay, so let me talk a little bit more about the GHC game. Here I'm going to spend some time showing you the connections of this problem to other combinatorial well-studied objects and tell you a little bit about our proof technique. Before I get started on the proof, I'm going to have to set up some notation. So I'm going to use P to denote the input distribution to the repeated GHC game. So this is the uniform distribution over points x, y, z, where each x, y, and z is an n-bit string and x plus y plus z equals 0. This is the input distribution to the n-fold GHC game. We want to say that given any strategy for the repeated game, it wins with probability at most inverse polynomial in n. And the way we're going to do this is to show the following. We're going to show that for all I less than equal to roughly log n, the probability of winning the ith copy conditioned on winning the first I minus 1 copies is small. So this is saying, even if you manage to win the first I minus 1 copies, the probability that you win the ith copy is small. Once you have this, if you multiply these inequalities for all I from 1 to log n over 2, you would get that probability of winning the first log n over 2 copies is at most 3/4 to the power log n by 2, which is at most inverse polynomial. Yes.
What is the classical value for this game?
The GHC game is 3/4.
So it's 3/4
Yes.
is the value, and you show that. Okay.
So yeah, here I'm fudging it. It's not exactly 3/4, it's 3/4 plus epsilon. What we managed to show is that the probability of winning the ith copy conditioned is at most 3/4 plus some small epsilon.
So you have to add a small epsilon.
Yeah,
Otherwise, it would be very.
This is too strong, yeah, to hope for. Yes, you're right. So yeah, I swept that under the rug, but you actually don't get 3/4, you get some 3/4 plus epsilon. So once we have this, we are done. If you could show this for all I from 1 to say order n, then you would actually prove exponential decay. Okay, so how do we do this? So there are some standard arguments in parallel repetition that allow us to simplify this expression. So if you consider this event winning the first I minus 1 copies, it introduces some new correlations. Basically, this event of winning a particular instance is going to introduce correlation between the answers and the questions of the players, but you can get rid of this new correlation. So just to keep in mind, this input distribution P already defines some correlations between the players' inputs. In addition to that, you get new correlations because of this event winning in the first I minus 1 copies, but you can get rid of these new correlations. And the way to do this is by fixing the answers and the questions to all the players in the first I minus 1 coordinates. I'm not going to go into the details of how this is done, but once you do this, the advantage is that you're left with a product event across the players' inputs. So once you do this, it suffices to prove the following statement. For all product events E1, E2 times E3, where E1 is an event on Alice's inputs, E2 is an event on Bob's inputs, and E3 is an event on Charlie's inputs. For all such product events that are not too small, that is, the measure of this event is at least 1 over poly n, you want to show that probability of winning some instance conditioned on E is at most 3/4. So at the back of your mind, you can think of E1 as basically fixing the questions and answers to Alice in the first I minus 1 coordinates. E2 fixes the questions and answers to Bob in the first few coordinates, and similarly E3 does it for Charlie. But for the rest of this talk, you can just imagine E1, E2, E3 as just being arbitrary events such that their measure is large. Okay, so this is what we're going to be proving for the rest of this talk, and this suffices to show polynomial decay on the parallel repetition. If you could show this for events such that measure of E is at least exponentially small, that is, it's at least 1 over exponential in n, then you would get exponential decay. Okay, so let's see how to do this. The idea is going to be the following. We're going to look at this distribution P conditioned on E, and we're going to show how to embed the GHZ game into some coordinates of P conditioned on E. I'll formally define what embed means, but I hope it's roughly clear what it's supposed to mean. So here is the high-level proof overview. You want to show that for large product events E, you can embed the GHZ game into many coordinates actually of P conditioned on E. We just need one coordinate, but we'll actually show that you can embed the GHZ game in many coordinates. And the way we do this is as follows. We first study some simple distributions which very clearly embed the GHZ game. We then approximate P conditioned on E by a mixture of simple distributions. And finally, we show that most of the simple distributions in this mixture actually embed the GHZ game in many coordinates. So this is the high-level proof overview. Let me talk a little bit about simple distributions. So what are our simple distributions? Our simple distributions are bowtie distributions. So to describe what a bowtie is, let me depict this problem in the language of graphs. So consider a bipartite graph. On the left side, put all possible Alice's inputs to the n-fold game. On the right side, put all possible Bob's inputs to the n-fold game and connect every possible input of Alice to an input of Bob. So here, the left side goes over bit strings of length n. The right side also varies over bit strings of length n. And you connect x, y for every x and y. You label this edge x, y by the label x plus y. You can think of the edges of this graph as basically inputs to the GHZ game, to the n-fold GHZ game. So an edge x, y corresponds to the input x, y, x plus y. So the edges of this graph are in one-to-one correspondence to inputs to the n-fold GHZ game. Each input of Charlie defines a perfect matching in this graph. So for every possible input z to Charlie, connect x and x plus z. This defines a perfect matching. If you take two different inputs of Charlie, you get two different perfect matchings. And what you get when you combine these perfect matchings is a bowtie. So a bowtie is basically this complete bipartite graph on 2 by 2, such that two of the edges come from one matching and two of the edges come from another matching. So this is a really fundamental concept for us. Any questions about what a bowtie is? So our simple objects are going to be bowtie distributions. So by a bowtie distribution, we just mean the uniform distribution on these four elements. So recall that you can think of these elements as either edges in a graph or as inputs to the n-fold GHZ game. So often I'll use these things interchangeably. So this is the bowtie distribution. Already you can see that something like the GHZ game is going on. So imagine that the verifier samples x, y, z uniformly at random from the bowtie distribution and sends x to Alice, y to Bob, and z to Charlie. This is very reminiscent of the setting of the GHZ game. And in fact, you can make this more precise. You can show that the bowtie game are kind of precisely the GHZ distribution, but embedded in higher dimensions. So more formally, consider a bowtie x0, x1, y0, y1, such that x0i differs from x1i. Then in the ith coordinate, you can show that these 4 points look exactly like the GHZ distribution. Without loss of generality, this is what a bowtie looks like. So in the ith coordinate, you have the GHZ distribution, and every other coordinate is just a deterministic function of this ith coordinate. So this is a bowtie that embeds the GHZ game in the ith coordinate. This means that any strategy that wins the ith coordinate of the bowtie distribution actually gives you a strategy that wins the GHZ game, in one coordinate. So any questions about this? Okay, so here is our main lemma. We show that for any large product event E, you can approximate P conditioned on E by a convex combination of bowtie distributions. Let's see what this looks like in the language of graphs. So now you take the same bipartite graph as before, but you only restrict your edges to be those that are in E. So recall that this event E defines a collection of inputs to the n-fold GHZ game, and we just look at all those edges that are in this event. This defines a subgraph of the complete bipartite graph on 2 to the n by 2 to the n. This distribution P conditioned on E basically corresponds to the uniform distribution over these edges. And because this event is large, we know that this graph has sufficient density. And what we're trying to do, what this main lemma says is that looking at the uniform distribution on the edges, you can actually approximate them by some distribution over bowties. So this is our main lemma. Now let me present some connections of this problem to combinatorial objects. So to do that, I first need to talk about some simplification of this bowties. So it turns out that you don't need actually to study bowties, but you just need to study these Z-shaped objects where you just have these three edges. It turns out that whenever you have these three edges, the fourth edge is also present. And this really comes from the fact that these events are product events. So the claim is that when you have an object like this, when you have two blue edges and one green edge between, then the other edge must also be present and it must be green. So this just follows from the product structure of these events. So basically what this is saying is that you can get away with looking for simpler objects, namely these Z-shaped objects, because they will imply that the bowtie is actually present. Okay, so what are we trying to do here? You have a graph, it has a sufficient number of edges, and we want to find objects like these. We want to approximate the uniform distribution over the edges by a mixture of distributions over these types of edges. So the first question to ask here is, can we even find this object in this graph? So abstracted out, here is this combinatorial question. You're given a subgraph with at least inverse polynomial density of edges, and you want to ask if it contains an object like this. This turns out to have connections to the Raz-Semeredi problem. So in this problem, this is a combinatorial problem. This asks, what is the maximum number of edges in an n by n bipartite graph such that the edges can be partitioned into n induced matchings? And the connection between this problem and this is the following. Suppose it was the case that the number of edges in our graph was less than this Raz-Semeredi number, then it could be the case that the matchings defined by each of Charlie's inputs are actually induced matchings. In particular, there is no cross edge in any of these matchings, in which case we would not be able to find even a single bowtie. So our problem is in some sense a special case of this Raz-Semeredi problem. And unfortunately, the bounds on this Raz-Semeredi number are not good enough for our purposes. So the only result we know is that if a graph has at least these many edges, then you can find a bowtie. But the number of edges we have in our graph, which is much smaller than this. So what we are going to use additionally is the fact that you have a product event, and we're also going to be using something about the Fourier coefficients of this event. We're going to say that if the Fourier coefficients are small, then everything actually works. So there is another combinatorial problem that is connected to our question, which is the corner problem. But I'm not going to go into too much detail. But basically, finding these bowties is similar to finding corners in sets. And just as before, the bounds that we have on this corner-free set problem are not strong enough to give us the parallel repetition theorem that we're looking for.
What bounds you need?
Yeah, so okay, so let me just say. So you want to find what is the largest possible density of a set that does not contain a corner. And this set is a subset of f2 to the n times f2 to the n. And the best result we have is 1 over log c to the n. But actually what we want is 1 over poly n. Okay, so yeah, the takeaway from these two slides is that in order to find these bowties in a large graphs, this is connected to various combinatorial problems, but those combinatorial problems don't have good enough bounds for our purposes. But what we're really going to use is the fact that these edges actually come from some product event. There is more structure to these graphs. They're not arbitrary subgraphs. And not only that, we'll use some assumptions on the Fourier coefficients of the events E1, E2, and E3. We'll then remove the assumption by showing how to reduce the Fourier coefficients of an event. But let me just say that we use some Fourier analytic techniques to argue this. Our main lemma. We show that if you have this graph that comes out of events whose Fourier coefficients are small, then you can approximate the uniform distribution over the edges by the following distribution. Basically sample a random bowtie in this graph and return a random edge inside this bowtie. This distribution is going to be close to the uniform distribution over edges in this graph. Yes.
What are the Fourier coefficients of sets of a set?
So you think of E1, E2, and E3 as a subset of 0, 1 to the n, or you think of it as a indicator function. So Fourier coefficients are just the usual standard Boolean hypercube. So your characters are like product of coordinates.
But it's for these three separately.
Yes.
So all three sets, each of the sets has their Fourier coefficients, and they have to be small.
Yes.
Meaning that the
So maybe I can.
solution is kind of peaked or not peaked. Meaning they're peaked or something. And way of saying that the E1 is pretty uniform. In some sense.
I'm sorry.
Does it mean that the E1 is pretty uniform?
Yeah. So what it means that it has no correlation with a hyperplane over F2, loosely speaking.
No correlation with what?
With a hyperplane. So by hyperplane, I just mean like, so if you look at this function product of xi, so right now I'm switching to the -1 world, and you look at linear functions, so to speak, linear in the F2 sense. So Fourier coefficients being small just means that E1 has very low correlation with F2 hyperplanes. By F2 hyperplanes, I just mean take linear functions over F2. This function E1 has very little correlation with any linear function over F2 to the n.
Can you give an example of a set like that?
Pretty much a random set will have low correlation with yeah.
Thanks.
Yeah. Yeah, if you've seen the BLR test, it kind of works on a similar principle.
Sorry.
If you've seen the BLR test, testing for linearity of function,
But for what?
Yeah.
Linearity?
yeah, testing whether a function is linear or not, it sort of has this idea.
Okay.
But yeah, I mean, pretty much any function is very far from being a linear function. So yeah, assuming that, yeah, so let me just quickly to answer your question. If you assume that the Fourier coefficients of A, B, and C are small, then you can do some Fourier analysis, which is actually really simple, to say that to derive useful properties of these events. And the way to ensure that the Fourier coefficients are small is just every time you find a linear subspace which has very high correlation with E1, you sort of break up E1 into cosets of this subspace and continue. So this is pretty much what I wanted to tell you about the proof overview. So yeah, so any questions? Yes.
Going back to the definition of connector game and those related concepts, can you provide some intuition for why the support was so important, given that the support is a discontinuous function in your red, but the value for games is continuous?
Yeah, okay. So why do these things only depend on the support of mu and not mu? Well, you can look at any mu as a kind of a convex combination of the uniform distribution over the support plus some other junk. So really, if you can prove that, so you have a mixture of distributions, and with some probability or actually the uniform distribution over mu, if you can prove parallel repetition for the uniform distribution over mu, then just because it's a mixture with some non-zero probability, you're actually going to be playing this uniform distribution in many coordinates. So that's the intuition. Does that answer your question? Or maybe I can.
Yeah, I mean, but what's wrong with the intuition? The support is discontinuous function of mu. So when you have one probability that's just very small, then basically that input is almost never going to occur, but changes the support.
Yeah, so actually the value depends on this degree of discontinuity. So if you have some probability p, your final bound on the parallel repetition value is going to depend on like 1 over p. So it's going to get worse as p gets closer and closer to 0. Yeah. So when I say support, I just mean that, we're talking about constant finite probabilities. So basically it's the same thing, just ignoring these constants. But yes, you're right. It does depend on the probability of the smallest possible probability of any point.
More questions? We didn't applaud. Should first applaud. More questions?
So for example, if would like progress on the corner problem, for example, immediately give you this result, and even with exponential parallel repetition, or is there like other hurdles on the way?
That's a good question. So there are two things you could ask. One, does this say anything about the corner question? I don't know about that because you have a lot of structure on these events. What about the other way around? That's possible, but again, so the corner problem just says how to find one bowtie, and that I don't see how it immediately implies this. Maybe if you look at all possible inputs and just restrict to the inputs where the strategy wins, and then you're trying to find a corner, or actually you might need more than a corner. You might need a square if you see what I mean.
Yes.
So maybe if you make progress on that question, then it's possible. Yeah, but it's very much possible that there are other combinatorial objects that would have implications on this GHG game. Yes.
What's the exact bound you have on the GHG game?
It's 1 over poly n, but
Can you say more, Lena?
I wish I could, but it's some large constant, 1 over n to the 100, I think, in our paper.
But it would be good to write it down because I think it's very relevant for experiments. I mean, this year's Nobel Prize, which is given out in 2 weeks, it will go to precisely the GZ game.
Right.
Right. The C of GZ, and for the experiments that verified this. And if now you have this parallel repetition result, you could really carry out. I don't actually know if they did experiments on the GZ state, what the status is there, but you could definitely improve because right, I mean the problem is you do these experiments and then you have some noise and so on, and then it's sort of like you have this classical thing which is 75%, and then that the quantum value is 1, but there's some noise that will bring it down in practice, right?
I see.
So if you can repeat this and then amplify the value, it's very relevant, I think.
I see.
And maybe therefore actually would be very good for this game particularly to know exactly like your bound.
I see.
How fast it go down.
I see. I think our technique probably will give at best 1 over square root n or something like that.
Yeah,
but I don't know.
It doesn't matter in that sense, but just to know what it is.
Well, I think the correct answer should actually be exponential in.
Yeah, I understand.
Yeah.
But
I see.
There could be experiments that will actually use your results.
I see. That's interesting.
And when they want to use it, it would be good to know.
I see. Yeah, maybe I can ask you more about it. It would be very interesting to see actual application of this.
Questions? Okay, we're happy. Thanks.